Bona tarda i benvinguts a aquesta primera sessió del cicle de conferències públiques de l'IN3 de la UOC. Crec que és tot un honor per a la nostra universitat poder comptar amb aquesta primera sessió d'aquest cicle amb el professor Wiebe Bijker, a qui vull agrair la seva disponibilitat per atendre la nostra invitació, tenint en compte especialment que té una agenda d'activitats internacionals molt apretada. So thank you very much for accepting our invitation. De fet, com alguns dels presents saben, el professor Bijker ha estat uns dies a la UOC col·laborant amb l'IN3 en la formació dels nostres doctorants en un taller sobre l'estructura de les tesis doctorals que va tenir lloc ahir a Castelldefels. En Wiebe Bijker és professor de Tecnologia i Societat a la Universitat de Maastricht, als Països Baixos. És enginyer en física aplicada per la Universitat Tècnica de Delft i va estudiar també filosofia a la Universitat de Groningen. Va obtenir un doctorat en Sociologia i Història de la Tecnologia a la Universitat de Twente, als Països Baixos també, i actualment és cap d'estudis del màster de recerca sobre cultures de la ciència i la tecnologia a la Universitat de Maastricht. Ha estat president de la Society for Social Studies of Science, que, com alguns sabeu, és l'agrupació acadèmica internacional més important en l'estudi social de la ciència i la tecnologia, i ha estat president de l'Escola Holandesa de Recerca sobre Ciència, Tecnologia i Cultura Moderna. Actualment és membre del Consell Executiu de SHOT, la Society for the History of Technology, la societat també internacional més important en la història de la tecnologia, i és editor de la sèrie de monografies Inside Technology que publica MIT Press. Al llarg de la seva carrera ha rebut diversos premis internacionals, entre els quals puc esmentar el Premi John Bernal per la seva contribució destacada al desenvolupament dels estudis de ciència i tecnologia. Encara que com a mínim alguns de vosaltres ja coneixeu la seva trajectòria i la seva obra, m'agradaria ressaltar-ne breument un parell de coses. A mitjans dels 80, juntament amb Trevor Pink, va crear un dels models d'anàlisi més influents per a l'estudi de les interaccions entre la innovació tecnològica i el canvi social. El que ara és àmpliament conegut com a model SCOT, Social Construction of Technology, va significar llavors la confluència de dues corrents d'anàlisi fins aleshores força independents i separades, de fet, per l'oceà Atlàntic. D'una banda, la sociologia del coneixement científic d'origen britànic i europeu, i de l'altra, la història de la tecnologia desenvolupada als Estats Units per autors com Melvin Kranzberg o Thomas Hughes, com a disciplina una mica independent de la història de la ciència. Com és sabut, una de les primeres presentacions públiques d'aquest model va ser a través d'un article sobre la història de la bicicleta a finals del segle XIX, un article seminal al que gairebé tothom es refereix ara informalment com l'article de les bicicletes, que ha tingut un gran impacte i continua sent, gairebé després de 20 anys encara, un dels més citats en l'àmbit dels estudis de ciència i tecnologia. De fet, donat que els estudis de ciència i tecnologia es recolzen fonamentalment des del punt de vista metodològic habitualment en estudis de cas, és un fet, diguem-ne, habitual associar l'objecte d'aquests estudis als seus autors. I així, doncs, Michel Calon és l'home de les vieires o dels cotxes elèctrics, John Lowe és el de la navegació dels conqueridors portuguesos, Trevor Pink el dels neutrins solars o Donald Mackenzie el dels míssils nuclears. En aquesta tradició, Wiebe Bijker és, sens dubte, l'home de les bicicletes i, de fet, pel que m'ha explicat aquests dies, hi ha molts anglosaxons que es troba pel món que pensen que això li ve donat pel seu cognom, perquè pensen que el seu cognom significa ciclista en holandès, i ho pensen simplement perquè la seva pronúncia s'acosta molt a la paraula anglesa per dir ciclista, que és biker. El fet és que el seu cognom és una vella paraula holandesa que significa, de fet, apicultor i no ciclista. Tot i que s'ha de dir que aquesta teoria de la determinació professional a través del cognom no la podem descartar del tot perquè, de fet, a casa seva, al seu jardí, té uns quants ruscos d'abelles que, per cert, produeixen una mel de molt bona qualitat. Però com en la resta d'autors que he esmentat, Wiebe Bijker no s'ha limitat només a les bicicletes en els seus estudis de cas, també ha publicat treballs importants sobre el fluorescent, la baquelita, les barreres antimarea holandeses, l'arquitectura o l'urbanisme, l'Eixample de Barcelona, per exemple, o la nanotecnologia, per posar només alguns exemples. Aquests estudis han estat publicats en obres com The Social Construction of Technological Systems, Shaping Technology Building Society, of Bicycles, Backlights and Bolts, Towards a Theory of Sociological Change, que són, sens dubte, obres de referència obligada pels que ens dediquem a aquest camp dels estudis de la ciència i la tecnologia. Actualment, entre altres projectes, treballa en un estudi sobre tecnologia i desenvolupament en el context de la producció tèxtil contemporània a la Índia, i em sembla que farà alguna referència en la seva xerrada d'avui, i sense més preàmbuls us deixo amb la seva paraula i recordo el títol de la seva xerrada, Vulnerabilitat en les cultures tecnològiques. Moltes gràcies.
Good afternoon. I could understand that much that I can warn you that I'm not going to speak about bees and honey. I want to make 3 points about vulnerability. Currently, my research is one way or the other related to issues of vulnerability and risk. As Eduard mentioned, a lot of research is at the moment related to the role of science and technology in India and in Africa. If you're interested, I'm happy to go to those issues after the lecture in the question and discussion time. I will now mainly use an example from the history of internet to keep close to your own teaching and research program, and an example from a recent involvement of mine in making politics in the Netherlands, politics about how to design a policy for nanotechnologies. I want to make 3 points. The first point, that vulnerability, I'm going to make an argument that we should try to understand vulnerability through understanding it as part of a technological scientific society. My argument will be that if you want to understand vulnerability in any way that is relevant for the issues that we have today, then you have to think about our society as what I will call a technological culture. The second point is that I will argue that vulnerability is not just something negative, maybe even a little bit positive, but certainly inevitable. So it's not something that we should at all costs try to weapon ourselves against, defend ourselves against. And the third point, and that's mainly the point where I will use the nanotechnologies example, is that I think there are ways for our modern societies, and I include Indian emerging economies, African developing economies in that, there are ways of handling that governance if we draw on, say, the insights of STS, science, technology, and society studies. So the first example, particularly drawing on the work of Janet Abatzi, an American historian of technology, wrote a book about the history of internet. And I want to compare, and they are in these 2 columns, I want to compare 2 protocols to make a computer network. 2 protocols to link computers to each other. TCP/IP on the right hand and X25 on the left hand, TCP/IP and X25 on the right hand. Both protocols work very well. So there is no reason that one is better than the other, and that's why one was developed and substituted the other. It's not like that. Both work, and actually we all use both almost on a daily basis. TCP/IP is used when we send emails to each other, when we go to the internet, visit websites. X25 is used when we, for example, get money. When we get money from an ATM machine, or when we book a train ticket through the internet or a flight ticket through the internet. The computers of the travel agencies, the computers of the ATM machines in the banks, they are linked to each other through the X25 protocol. So if we want to understand why 2 protocols exist rather than only one, the best, then the answer that one is better than the other doesn't work. So there must be another reason. I will argue that the best way to understand these 2 protocols is by analyzing the cultures in which they emerged, in which they were constructed. And I'll go through several elements by going from the top to the bottom of these 2 columns. TCP/IP was originally developed by the laboratories of the American military. The big laboratories that developed the atomic bomb, the missiles, they needed to link their big research computers to each other, primarily to send data files that came from experiments to the other laboratory so that the other laboratory can work on it. ARPA stands for that network of the Defense Department of the United States, linking those very sophisticated, very, say, top-end physics and engineering laboratories to each other. X25 emerged in the PTTs. Most of you have an age to remember what PTT stands for. The Post, Telegraph and Telephone companies of our countries. In almost all countries, those were monopolies. In most cases, state monopolies. It seems a long time ago. But that character, to a large extent, determined the culture of the PTTs, that monopoly, that state service function character. And that contrasts with the culture in the military laboratories. For example, let's focus on the technology. Evidently, then and now still, the computers of those laboratories were the absolute top available. The most, and they still are, of course. And then they were the most powerful, the most sophisticated computers available. That also applied to the users. I mean, those users, engineers, physicists, computer people, if anyone was able to tinker with the computer, if necessary to tinker with the protocol because something went astray, then it would be those people working in those laboratories. Here, it's exactly the opposite. There was a long tradition of the PTTs, now particularly thinking about their telephone exchange networks, where their image of a network was that the telephones were very simple, not to say stupid machines. The old telephones, you may remember them or have seen pictures, big, often black, heavy, Bakelite machines. They didn't even need power. There was no battery. You didn't need to plug them into a mains. They just had a spring to dial. I mean, that's where the word dial comes from, to dial the number. And that was all. Very simple machines. And the PTTs also assumed that the users of those telephones were equally simple, if not stupid. I remember that when I was in primary school, we were actually taught how to use the telephone. That was only in the 1960s. But even then, the PTTs thought that the users of their telephone needed to be taught how to use the telephone. A big bus arrived at the front of our school. We were all very excited. And then in the classroom, there was a telephone there and a telephone there. And we had to call. We were allowed to call from that table to that table so that we understood how that works. That is the dominant. That's the dominant culture of the PTTs. Very, very stupid machines and people on the outside that need to be connected, and a very clever, very sophisticated, automated telephone exchange in the middle. Later, electronically. In the old days, first women who connected physically with wires, connect the telephone in one address to another address. But by the time that we were talking about the X25 protocol, it was all automated and electronic. Let's have a look at the kind of problems and the kind of vulnerability that both organizations had to deal with. TCP/IP was very much developed with the Cold War in mind. What they wanted was a network that would continue to operate after a nuclear attack by the Soviet Union on the United States. What they wanted is that if a bomb would hit, say, the East Coast, Washington, New York, that the West Coast, California, the laboratories in the Nevada desert would continue to be linked to each other, that the network would continue to work there. So the network somehow had to be able to take care of itself. That was a very strong design requirement of the left-hand protocol. Flexibility. They also wanted multiple networks with that could then be connected to each other. So within the laboratories, there would be multiple networks that needed to be connected to each other. And they basically wanted a fairly simple network that was linked to the Cold War ideal. We don't want complicated things that then may go wrong. There are enough threats from the outside. We don't want a very complicated, and because of that complication, vulnerable network itself. Let's keep it simple. Sometimes things may go wrong, but the users were so sophisticated that they could mend that themselves, was the reasoning. So let's go for simple and flexible. Here, it's the other way around. I'm not sure about the postal system in Catalunya now. Certainly in the Netherlands, this seems a long time ago. But there were these days, the 1970s, that when you posted a letter at 5 o'clock in the evening, there was a 100% guarantee that it would arrive any place in the Netherlands the following morning at 9 o'clock. There was a true belief, a belief in its own standards of what is the word? Trust. What is the word? You could trust the PTT. They really made a pledge that whatever you put in our bus, we will deliver the next morning at 5 o'clock. They had very high standards of reliability. They could afford that because they had a monopoly. They didn't have to compete in terms of prices and costs. They just set the standard. There was only one telephone company in every country, the national PTT. Reliability in those terms was a very high requirement. And they put that into their requirements for X25 too. So the culture of the PTTs called for a very reliable, very sophisticated, possibly complicated network for very dummy end users and end computers. The TCP/IP culture, the ARPA culture, called for a very simple, flexible, possibly a little bit more vulnerable network, but that could be mended by the users, the engineers, the scientists in the laboratories. This ends in two very different technologies, very different technical solutions for the problem how to link computers to each other. TCP/IP is a datagram network. X25 is a virtual network, and they are completely different. The datagram network is a network, and most of you may know this, but I'll briefly explain it. What it does, when I send an email to you, the protocol cuts my email in packages, in datagrams. Every package gets the address of your computer, and it's kicked out on the network. Basically with the message, good luck, you sort it out for yourself. You have the address, you just check all the computers that you pass by until you find the right one, and then you wait for your mates to come. And every package is kicked out on the network, and they all find their way. And some may go through this route, and others may go through that route. The idea being that if half of the network is blocked, they may try to go there, but then bump back. It's like balls in a pinball machine, and then they gradually find their way through another route. But in the end, hopefully, they will reach it. Sometimes they don't, but then you resend it, or you fix the message because evidently something went wrong. That's a datagram network. And you can, I remember vividly a moment where there was a news item that one of the cables between India and Europe was broken, one of the internet, the data connection cables. And quite clearly there was a slowdown in the traffic, in the internet traffic between India and Europe. But not a complete cut. It just meant that all these datagrams need to find another way, a longer route, and it took them a bit more trouble to find their way, but they did find their way. The virtual network is a completely different solution. That very sophisticated, very highly developed central computer, mirrored after the telephone exchange, has a virtual map of the complete network that links all those computers to each other. You may have seen pictures of, say, a control room of a railway network, when at the wall of that control room is the whole stylized picture of all the railway tracks around that particular area, and dots of lights indicate exactly where all the trains are. It's stylized, but it's completely one-to-one online real picture of what is happening in the outside real world. That is also what X25 does. It has a complete map of the networks, and the protocol decides through which path that message is sent from computer A to computer X. And it's completely controlled from the beginning to the end. Now, the result, of course, is that if something happens to this central computer, then everything is out. So in that sense, it's much more vulnerable. It's more vulnerable that if you do drop a bomb on that X25 control computer, then everything is out. That's different on that side. Hardly anything goes wrong as long as the central computer works. Something may go wrong for completely unclear reasons in the TCP/IP protocol. And most of us have that experience once in a while. Something goes wrong, but we don't really know why. We just send it again, and then it works. Very different ways of dealing with the requirements of vulnerability. My conclusion, before I broaden the scope, my conclusion from the previous example is that if you want to understand how these protocols work, even down to the nuts and bolts of the code and the software and the hardware associated with it, you can only understand that by tracing the social shaping, by tracing the cultures in which those two technologies were developed. That's my first point. But I'm still on the first point, that vulnerability is to be analyzed as part of technological culture, and to do that, I will now broaden the analysis that I've given so far. I've talked so far mainly about artifacts. I've talked about the artifact of a protocol. That's a piece of technology in a way, a piece of software. There is a long tradition amongst engineers of dealing with vulnerability. That's called reliability engineering. They deal basically with artifact, with things, with nuclear reactors, with ships, that kind of thing. Gradually, the unit of analysis was broadened. From just only technology, there came attention not only by engineers, politicians, bureaucrats, but also by students of technology, first of large technological systems, I'll say a bit about it in a minute, then of society at large, and even of cultural dimensions like the identity of people, humans, individuals. Just in a few keywords, reliability engineering I mentioned. Charles Perrow, an American organizational sociologist, wrote a seminal book called Normal Accidents, and what he claims is, and I think very convincingly, is that large technological systems, and his examples are big oil tankers, air traffic control systems, nuclear power stations, very big systems, are so complex, are so tightly coupled, that's a key point, are so tightly coupled that accidents almost become inevitable, that accidents become normal. Because of the complexity and the tightly coupledness of those systems, we should be more surprised that no accidents happen than that sometimes an accident happens. Ulrich Beck further enlarges the unit of analysis by talking about, in his German concept, Risikogesellschaft, a risk society. His argument is that from, say, the days of industrialization, the days that were described by Marx theory, for example, our current days are better described by the risk that we run. So rather than class determining our fate at the moment that we are born, is the risk that we bear, either by living next to a chemical plant or in whatever, living in an earthquake-prone area, although that is a natural risk. It's risk that determines our fate. In the old days, you acquired power by acquiring wealth, by becoming rich, by owning means of production. In the new risk society, it's much more knowledge that will give you power. Knowledge will then, because knowledge allows you to cope in new ways with risk, somehow diverting risk to other people, controlling risk, organizing the means to diminish your vulnerability. The other point that Beck makes is that in a risk society, it doesn't make sense anymore to talk about national states. Risks are global. From the early days of nuclear power and the effects not only global but also over longer time stretches to generations that even haven't born at this moment, certainly continues with genetic modification, genetic engineering, nanotechnologies, as I will talk about later this evening. In that sense, the risk society is a very different society than the old industrial society, with those key concepts like risk rather than class, globalization, the key role of science and technology that creates risk. What I use from Manuel Castells is adding another further dimension, adding what I then call the cultural dimension, in addition to I know that Castells is a sociologist, but the sociological analysis of Ulrich Beck of society, Castells add with his network society analysis the dichotomy between the self and the net. That's where identity comes in, both of individuals as part of the network society, but also of groups. And the groups may be distributed. That's new in terms of a sociological concept. And a networking logic with all its inclusion and exclusion effects, but very differently from the old, say, peer group sociology, because the networking logic may not be, very likely is not localized in one place. So it's a very different style, a sort of cultural dimension that is added to the unit of analysis that broadly then brings me to the conclusion that we should talk about, and I want to talk about vulnerability in technological cultures rather than vulnerability in machines or in large technological systems or even in society. So that's my argument. That's point one, why I want to talk about vulnerability of technological cultures. That is part, this is a kind of footnote, it's part of a longer transformation within STS, Science, Technology and Society Studies, the field that I'm working in, which is summarized by this picture. The beginning of STS can be, I would like to identify in the 1970s and 1980s. 1970s, controversy studies, trying to understand the development of scientific knowledge by focusing on the controversy between scientists, the idea being then when we look at how scientists fight about the truth of a statement, that's where you can understand how the shaping of knowledge is actually happening. Laboratory studies were part of that. Let's look at that point and at that moment where scientific knowledge is created if we want to understand the processes by which that happens. In the 1980s, technology studies were added to that, very much in the same style of constructivist work. Maybe I should briefly explain what this constructivism means here. It means that rather than assuming that you can understand science, a scientific fact, as a discovery, as literally taking away the cover, peeping through the hole, and seeing the facts of nature down there, if you don't believe that picture, and we didn't believe that picture in the 1970s, then you have to come up with a different kind of analysis, a different theory about how scientific truth is created. and that is the kind of constructivism that I'm talking about. And that's the kind of constructivism that was created by the controversy studies and the laboratory studies, and then further extended to an analysis of technology. You could summarize this, I summarize this as a study of the cultures of science and technology. The local culture in the laboratory, the local culture in the workshop, the local culture in the manufacturing plant. The thrust that I'm now describing happened in the past 10 years and is a broadening of the agenda, a broadening of the research agenda, also a broadening of the unit of analysis. And from studying the cultures of technology, what I'm now arguing for is to study technological culture. Next slide will more elaborate what I mean with technological culture. The broadening of the agenda is in that left-hand corner. That agenda includes issues about democratization of our societies, the role of non-governmental organizations, the role of politics. If you cannot use the old idea of there are facts there and there are values there, the scientists bring the values to the the scientists bring the facts to the politicians add some values to the soup, and they decide. If that is too naive a picture, then you need to think about what now politics can be in this new conceptualization of studying a society. The role of scientific expertise comes on the agenda. I'll say much more about that later. As Eduard mentioned, much more STS research is now going on in the global south by colleagues in India and Africa, but also in collaboration with European and American colleagues. And my topic of vulnerability of technological cultures. What do I mean when I say we live in a technological culture? To my colleagues in the social sciences, it is an advice that they should not hope to understand modern society if not also taking into account the role of science and technology. And I think that even pertains to people who try to do musicology. If you want to understand modern music, you can't do that without understanding the role of science and technology. And that goes from iTunes and the way that shapes preferences and ordering of music to also the contents of modern classical compositions, where composers sometimes very explicitly reflect on the sounds of, for example, the industrial society. Compositions like that were already written in the beginning of the previous century. My argument being, if you want to understand our current societies, you have to also look into the role of science and technology as constituting those societies. But at the same time, the other side of the coin is an advice to the engineers. Don't hope to build any working machine, any working technological system, if you do not take into account how that system is embedded in a particular society, in a particular culture, if you don't also think about the social and the cultural dimensions of that technology that you're trying to design. So it goes both ways. If you take the statement, we live in a technological culture serious, then both on the social sciences side and on the engineering side, that has quite profound implications. Final slide on technological culture. So for me, it's just a shortcut for a modern society that cannot be understood without that role of science and technology, that has at least 4 conceptual consequences. The first being that if you really take that serious, if you really take seriously that technological culture is the unit of analysis, and that you cannot talk anymore about separately the technical scientific factors and the social factors there, but that everything is tied together, then you're in trouble. You're in theoretical trouble. You cannot anymore, which we used to do, you cannot anymore explain the social by you say make the social as a dependent variable and take the technical as the independent variable. Technical determinism describes the world by showing how technology determines society. Social constructivism, in its earliest forms, did it just the other way around. In both cases, there was a separate basket of technical factors and social factors, which very neatly allowed for that either technological determinist explanatory schemes or social constructivist explanatory schemes. If you take seriously the unit of analysis of technological culture, you can't do that anymore. Then there is one big soup of social and technical factors. Actually, you can't talk about social and technical factors anymore. There are socio-technical factors. So that's why concepts like co-production, co-evolution, two sides of the same coin are then used or are tried to develop explanatory schemes. That's very much at the front of the research because I mean, it's not as clear-cut as in the old days of separate dependent and independent variables how we have to do that job, but that is one of the consequences, that you have to look for new concepts like, for example, co-production of co-evolution to do that. Second point, second conceptual consequence, the distinction between what is technical, what is cultural, what is social, what is political, is not pre-given. That wasn't a basic idea of constructivism all the way. Rather than going into some problem with, in the back of your pocket, a list of what are the social factors or what are the technical factors, this says it's much more fruitful to go out into the world and see how people define a problem, how actors define a problem. If there's some problem in a shop floor, then it makes a huge difference whether that is defined as a technical problem and then given to the engineers to be solved, or as a costing problem, then given to the economists and the accountants to solve, or as a human resource problem, then given to the training people or the personnel people. How such a problem is labeled is much more interesting than to come there and already label it in a kind of a priori way. And the fight about how to define that problem, the negotiations about how to define that problem, that's where the real work happens. So that's the second conceptual problem. Looking at the world as a concept, as a technological culture, encourages you to look for those negotiations rather than assume that you already know how the world is carved up into different bits and pieces. Third element is that these construction processes, the construction of technical systems or the construction of social institutions, that is all symmetrical now, that continues forever. There's no reason why it would stop at a certain point. Users may pick up something and give it a new identity, and then that new technology may develop further. Email was developed by users, really more developed by users than by the people who first wrote it as a little add-on on the exchange of big data files. A similar point, the fourth conceptual point, these construction processes may involve a broad variety of people. Possibly anyone can be involved. In that little history of the bicycle that Eduard briefly referred to, women play a very clear role in that. Even anti-bicyclists in late 19th century England played a role in the development of the bicycle, and not just the engineers or the marketing people. Different social groups play a role in the development of a technology. That is one of the conceptual consequences of taking technological culture as a unit of analysis. My second point. Let's make a kind of conceptual analysis of that word vulnerability, just to set the theme. Most clearly, the most clear connotation is the negative one. Then vulnerable is the opposite to secure. It's related to terrible things like poverty, death, the destruction of buildings. on the positive side, the opposite is to be stagnant. If you move, if you develop, then you may be less vulnerable. So the opposite the connotation of that vulnerability is more associated to learning, to growing, to developing, to change, to being flexible. To understand those different aspects of vulnerability, I think you will now accept, after my first point, that I want to argue that you can better analyze that as when you pay attention to the way that we talk about technological cultures and the way in which technological cultures shape that vulnerability, and vice versa are shaped by those vulnerability. And I'll get to different styles of risk management and precaution in the last part of the story. To finish this point, evidently, the sort of basic meaning of vulnerability, the breaking down of computer networks, the breaking of dikes in Bangladesh or the Netherlands, the collapsing of buildings either by technical mistakes or by earthquakes, that is quite straightforwardly negative, and I don't want to change anything about that. The second observation is that vulnerability is also almost inevitable. You can't think of a modern society without the inevitable vulnerability. We are very happy, I mean most of us are quite happy with the mobile phones, and it helps to defend against certain forms of vulnerability. I mean, in the Netherlands you give your children a mobile phone if they have to travel a long way, either on the bicycle to school or in public transport, so that it makes them a little less vulnerable and they can call. But it introduces a new vulnerability. If the battery is out and they can't call and they are 1 hour late, then father and mother are extremely panicking. While normally, in the old days, they would just think, wow, the bus is 1 hour late. So the new technical system creates new forms of vulnerability that we somehow accept. It's the price that we're happy to pay to some extent, but definitely it's inevitable. So vulnerability is something that comes as an inevitable aspect of modern technological culture. I even think, though I'm a bit more tentative there, I even think that vulnerability has, in certain circumstances, some positive aspects. It does create flexibility. It creates flexibility, and because of the flexibility, the possibility and the opportunity to learn and to change and to develop new solutions to certain problems. It creates the possibility for development. I had another example drawing on my work in India, which was too much for the framework of this lecture, but we may go into that in the discussion where I argue that handloom weavers in India, who on the one hand seem extremely vulnerable because they don't have the big machines, they don't have the big capital, may now be in a situation where they more flexibly can react to the design requirements of high-end niche markets in Europe and the US, and because of their initial vulnerability and flexibility, in the end, may positively get out of the current textile market crisis. That's a very sort of brief summary, and I can't really solidly prove it, but I have a hunch that in addition to also being inevitable, there may be occasions where vulnerability is actually something positive. At least vulnerability is something much more subtle and complex than a purely negative concept that one way or the other we have to ban out of society. Let me finish on that note in this second point, a kind of counterfactual argument. If you think of a society that in no way is vulnerable, that has banned all forms of vulnerability, I personally find that the most frightening kind of society that I can think of. It's much more frightening than a political totalitarian state. It means that I can't make any mistake, and then there is something that blocks me making that mistake. Nothing can go wrong, or there's some technical or social system that stops me making that mistake and something going wrong. So it must be a completely stagnant, stifled, constrained society. That is the kind of idea why I think that being vulnerable actually does have some positive, or may have some positive effects. Okay, last part of the story. Now going to the more political issues. I'm going to argue that this constructivist approach, the way that I've outlined it so far, plus that focus on technological culture, will allow for a way of dealing with the vulnerabilities, the risks that modern science and technology creates. And I'm drawing on work by Ortwin Ren. I'll give you some other references in the last slide. And what I'm basically going to do is to sketch to you a risk governance approach, an approach to handle politically in a democratic way risks in our modern society. This is the summary. The big question is, how can we cope with these vulnerabilities? My example will be nanotechnologies, but it's exactly the same when we decide to in a big scale, reintroduce nuclear power, or the discussions about genetic modification at this moment. So that's the issue, how to democratically deal with the vulnerability that we are at the moment introducing into our societies. I will sketch you as a solution this model of risk governance. And the way that works is that the central argument is, let's try to identify these vulnerabilities, these risks, in different categories, and those categories then lead to a specific way of handling them. And then the problem is contained in such a way that I hope to show you we can deal with it in our democratic society. So that's how the story will run. This was developed by a committee on nanotechnologies for the Dutch government in 2006. And the Dutch government actually basically adopted that advice and is currently in the process of executing that policy. I'm happy to tell you more about that afterwards. This is the basic conceptual core. Try to identify situations of vulnerability, situations of risk, in 4 different categories: simple, complex, uncertain, and ambiguous. I'll give you an example drawn from nanotechnologies. I mean, you don't need to know any details about nanotechnologies, but just nanotechnology is a big umbrella term for all the science and technologies that deal with matter at the level of about 100 nanometer, which is pretty small. Let's put it like that. Some people would argue, well, that's what chemists did for centuries, didn't they? The difference is that there are now techniques to almost manipulate individual combinations of molecules. One way to get there is to come from the top end, so it's basically then the end of miniaturization from transistor to integrated circuit to smaller. The other way to get there is to get from the molecular part and to develop instruments to manipulate molecules into different things. That definitely creates privacy problems. For example, radio frequency identify RFID things that some of the people here are studying too. I learned yesterday from PhD students. They can be put into your skin. They can be put in all sorts of freight that is traveling around the world. They become so miniaturized that may create all sorts of privacy problems. We think, and we've argued to the Dutch government, that there is, certainly those problems are risky, and we need to attend to them, but there is nothing new about them. Basically, once you have identified that nanotechnologies may create certain privacy problems, you can deal with them in the normal way that other privacy problems are dealt with too. So you need scientific expertise, but it's basically all available. Complex problems are similar in the sense that all the elements are understood, but like in this case, the effects of nanotechnologies on the north-south relations, if you introduce nanotechnologies in, for example, India, how does that affect the trade relations to Europe? How does it affect the internal wealth distribution in India? Small pockets of relations are well known and are understood, but the complete problem is so complicated that you can't deal with it in a straightforward scientific matter. And that will come back in the next slide. The third problem, that's really something different. Their scientific knowledge is not adequate, is not complete, is not available enough. The example from nanotechnology is the toxicity of nanoparticles. There is something quite fishy going on there. There is something disturbing. We've all learned in secondary school chemistry classes that gold and silver are what we were taught inert materials. That's another way to say that they do not react, or very difficultly react. Which is another way of saying that they are not toxic. If they don't react to your skin, you can put jewelry on your skin. If you make nanoparticles of gold, then they seem to turn highly toxic suddenly. That's worrying. It's worrying because it's very serious scientific evidence that they turn toxic, but it's still not completely understood how, and under what circumstances, and what you can do with it. So this is an example where there is a serious indication of trouble, but the scientific knowledge isn't complete enough to deal with it. That's why it is in the box of the uncertain vulnerability. Now, the final category, ambiguous risk situations, there the problem is, again, very different. In the case of toxicity, there is basically no discussion that we don't want it. Basically, the value in society is clear. We want to ban toxic materials, full stop. The only problem there is that we are not scientifically certain about the quality of those nanoparticles, and that is creating the trouble. In the case of ambiguous problems, we don't even have an agreement in society where to go. The example is, for example, a human enhancement, implanting a memory chip in my brain. I would love it. The big family of my wife makes me remember names of aunts and sisters and brothers. And with a memory chip, I would survive the birthday parties much smoother than without the memory chip. But I mean, I suppose that you will recognize there will be lots of people, certainly fundamental Christian groups, who are vehemently opposed to such technologies and would describe it as tinkering with God's creation and tinkering with the integrity of the human body and clearly bystepping the bounds of what humans should do. So in this case, it's not only a matter of scientific uncertainty. No, a much more fundamental problem that we don't even have an agreement on where to move with society is what shapes that vulnerability discussion, that risk discussion. Now, if you accept this categorization, that has implications for how to deal with those problems. But I'll skip the middle column that characterizes the main style of dealing with those problems. Let me, for the moment, only focus on the last column, which describes who is invited to participate in discussions and in deciding on those problems and those issues. Now, in the first case, I have no hesitation to advise to just give that to the scientists. Don't bother citizens with it. Don't bother stakeholders with it. I mean, we don't take a vote on 2 + 2 is 4. We don't take a vote whether asbestos is dangerous or whether ionizing radiation, nuclear radiation is dangerous. That's what scientists are capable of dealing with. Let's just give it to them, and that's it. In complex problems, that's probably not enough. For complex problems, for example, the issue of what happens if we introduce nanotechnologies in Africa, although all the science is clear, the science clearly will depend on the perspective that you have. So that is the kind of problem where I think we should involve a much broader variety of scientists, recognize that scientists come with their perspectives. In this case, invite scientists, for example, from Greenpeace or the Meridian Institute to participate in addition to the mainstream university scientists. Evidently, by definition, scientists are not enough here, because the whole definition of that category was that scientific knowledge is incomplete. So there we need stakeholders. There we need explicit attention to economic, political, very different arguments in addition to scientific arguments. The balance, we need to take a decision whether we will go along with this nanotechnology development, although there are certain risks that we cannot map completely, but we may decide that we will still do it because the benefits are so huge that we don't want to run the risk of losing those benefits. So we want to include economic, political, and other elements. So we want to include stakeholders. But still, I don't think that it's really necessary to involve the broad public. They can leave it to the stakeholders and the scientists. In this case, there is no way that you can escape also involving the broader public. Not that that's easy. I'm not that naive, even though I'm Dutch. But the call there is to develop forms of public debate that somehow give a voice to the general public, somehow help, add an instrument to democracy, to have a much broader discussion about where society needs to go. Have a discussion about what we want with, for example, human enhancement. Now, you're definitely clever enough to realize that basically I'm begging the question with that nice previous slide, because who decides in which category a certain problem fits? I think we thought, the committee that advised the Dutch government thought that then can only be a broad committee that again has a heterogeneous composition. That should include the broad variety of scientists and stakeholders and spokespersons for the general public. In however way you want to organize it, but that needs to be broad. If you give that central decision power about the categorization to only scientists, then you are again back to technocracy. And if we don't want that, and I don't want that, then you're bound to find some solution of doing the triage, doing the decision of where a certain problem fits in that categorization by a broad committee. And we have advised that such a committee would then report every 2 years, because this is a very dynamic field. Some problem, for example, these nanoparticles, synthetic nanoparticles, may now be in the box of uncertain problems. They may, because of scientific development, may move to the complex particles, or maybe even move to the ambiguous box. There will be lots of development, so that committee should regularly report about the new state of affairs in this case, nanotechnologies. And then depending on the characterization, they would send that problem to the different pockets of decision-making or advice that a certain country or the European Union has. These are examples that exist in the Netherlands, but something like that exists in most countries, and otherwise my plea would be would need to be developed. A final remark, and then I'll conclude. On the one hand, this seems quite naive that you can do something like that. On the other hand, I think it's about the only thing that we can do now. I mean, the alternative would be to not talk about it, not have a broader debate if you're talking about for example, human enhancement problems, and then run into trouble, for example, the way that we, being the scientists, ran into trouble in Europe with biotechnology. There's a quite common understanding that the too optimistic presentation of biotechnology, and particularly genetic modification, about 10, 15 years ago, created a quite violent reaction amongst the European public, but so violent that there was hardly any proper discussion possible anymore. Also stopping it stopped some bad developments, but it also stopped some beneficial developments. If we don't want something like that, then we need to find new democratic instruments, and this is a proposal for that. And it was, it worked in the sense that at this moment there is the feeling both on the side of the scientists and the engineers, and on the side of the action groups and the NGOs, that at least this creates a kind of map, a kind of even playing field where it is possible to raise issues, to discuss issues, and not a priori define things out of the agenda. To conclude, what I've tried to argue is that if you take that constructivist perspective, if you start very minutely with, say, the bicycle, which I didn't explicate, but for me that's where it started, you enlarge the agenda by looking at our modern societies, recognizing the role that science and technology have in creating risks and vulnerability, but also have in coping with vulnerability. Then on the agenda come new questions about politics, about scientific expertise, about how you can use the expertise of stakeholders, the expertise of the general public, how we should enlarge and enrich the basically 19th century constitutions that we all have, constitutions that were created for a world that didn't have the science and technology that we now have. So develop instruments to deal with that new form of vulnerability of technological culture, for example, in the form that I just showed you. Whether that works, we are trying to find out at the moment, but at least it's one way to move forward. Thank you very much. And those are